Right? We are now looking at nuclear processes. Right? As I say, if you Google it, nuclear processes, that's what you see the picture. Right? We'll learn how to write nuclear equations for alpha, beta, and gamma decay. Okay, what's a nuclear process? Nuclear process occur whenever the number of neutrons or protons or both in the nucleus is changed. Right? Anything change in the nucleus where the number of proton and number of neutron are different, then it's a nuclear process. Example of nuclear processes: fission, fusion, radioactivity, nuclear reaction. It is usually called artificial radioactivity. Right? Nuclear reaction. In nuclear physics, nuclear reaction is a process in which two atomic nuclei or nuclear particles collide to produce a product different from the initial particle. Right? So it's collision between two nuclei, and it produces the result. The product is different from the original particle. Example, we have alpha. You send alpha to collide with nitrogen. Right? And what are the product? Right? Bombarding nitrogen atom with alpha particle. The product is oxygen and proton. These are the product. So this is an example of a nuclear reaction. In principle, a nuclear reaction can involve the collision of two or more nuclei or subatomic particles, but the probability of three or more particles colliding at the same time is extremely small. In such an event, is exceptionally rare. Right? So it's usually between two atoms colliding, two nucleus colliding. Three is usually very rare because we cannot see, we cannot aim at it. We just send them to collide, that's all. Alpha particle, sending alpha particle from radioactive decay towards nuclei, nuclei was the first step to learn about atomic structure, right? How the atom is built up. The next step, what happens if we send an alpha particle into the nucleus of atom? We send, remember alpha is positively charged. You want to send it, before that we send it low energy, right? It's energy from decay. So it doesn't have the energy to go into the nucleus. And now we want to accelerate the alpha particle. It has greater energy to go into the nucleus. We need to accelerate the charged particle to higher kinetic energy. At higher energy of alpha particle, Rutherford scattering formula breaks down. That one you don't need to worry, the mathematical part. Right? Remember, the two positive charge are repelling each other all the time. And the repulsive force become greater and greater as it come nearer and nearer to each other. So alpha particles get much closer to the target nucleus. Right? Alpha particle is positive charge. Target nucleus is also positive charge. So perhaps new short-range force operates over the short distances and change the interaction. Right? So we believe that as it approaches the nucleus approach, there is some short-range forces acting to allow the alpha particle to enter the nucleus. Nuclear reaction occur where a new nucleus is formed and the resultant emission of charged particle. Why are electrons not used in alpha scattering experiment? They are small mass and thus easily deflected by electrons of the atom. In chemical reaction, we combine different atoms to form a new chemical or new, right? Two atoms combine. can be of different kind to produce a new chemical or compound. Can we transform an element to another element? Right? First thing we can. So we are going to go into rules for writing nuclear equation. Atom X react with atom Y to produce W and V. These are nucleus representing the nucleus of X, Y, and produce W and V. Conservation of nuclear number. Total mass number or nuclear number is constant before and after the reaction. Means we add the two, A plus B, not B equals to C plus D. Conservation of charge. Total charge is constant before and after the reaction. Right? That means we add N plus P before, F equals to Q plus R after. In all nuclear reaction, nuclear number is conserved, charge is conserved, mass energy is conserved, momentum is conserved. Okay, just for your info, comparing nuclear reaction and chemical reaction. Nuclear reaction driving force is the loss of mass. Chemical reaction, bond breaking and bond making. Nuclear reaction, mass and energy is conserved. Chemical reaction, conservation of mass. Nuclear reaction, the nuclear energy involved is 10 mega electron volt. Whereas for chemical reaction, the ionization energy is about 10 electron volt. Right? It's about the difference in energy is about 1 million times, or 10 to the power 6. Produce gamma photon. Chemical reaction produce ultraviolet photons. Nuclear reaction interact to produce new atom. Chemical reaction interact to produce new compound. Right? Nuclear reaction produce new atom. Chemical reaction it produce a new compound. Okay, radioactivity. Right? We can draw picture, but usually we won't draw picture, that take too long. So we write equation. It's the result of the decay or disintegration of unstable nucleus. Right? The original atom or nucleus is called the parent, unstable. Right? Unstable is radioactive. The product is called daughter. The emitter particle is called alpha. Emitter particle is called the emitter particle. That's the daughter nucleus. That's the parent nucleus. By the emission, so radioactivity is the result of the decay or disintegration of an unstable nucleus. This nucleus is unstable by emission of particles or particles, and sometimes accompanied by emission of gamma rays, right? Alpha particle, and then it can be sometimes with gamma ray also, to form usually a more stable nucleus. Right? You want to form a more stable nucleus, so that's the daughter, and there's a symbol that there's radioactive material around the place. Radioactive decay of nucleus is essentially independent of environment of the nuclei, right? Whether the atom is combined with another atom, or it can be whether it's hot or cold. Parent and daughter nuclei are usually different elements. Different terms are used: decay, disintegration, and transmutation. It's a spontaneous and random process. Okay, artificial radioactivity. This one we example, the first nuclear reaction was performed experimentally in 1919 by Rutherford, who exposed nitrogen, that's your nitrogen, to alpha particle, helium nuclei, from a radioactive element radium, producing oxygen and product. So you need to know how to write the formula. Right? There's nitrogen, there's alpha particle, there's oxygen produced, and proton. Right? Fission reaction, a very heavy nucleus, that's a heavy nucleus, spontaneously, it can either by itself or it can absorb a light particle, usually a neutron. Right? There's a neutron, that's a heavy nucleus. Right? It can be by itself or it accept a neutron, splits into two, that's a two, or sometimes three. Right? And alpha decay is not called a fission experiment. It's not called fission, but fission is very distinctive feature. Heavy, break down into two smaller one, less heavy, lighter element, and produce other particles. Right? Usually it's neutron. Right? From here, we can calculate. We add the A, that's the initial A, 235 plus 1, minus 92 minus 141 to calculate what is coming out from here. And then delta Z, the difference initially is 0 plus 92, then 56 plus 56 and 36 minus that is 0. So it tells us that the particle that's emitted is uncharged. So can you work it out? What is the particle? Yep. What's the particle?
Uh, neutron.
Yeah, it's a neutron. How many neutron?
No charge.
I know how many neutrons are emitted. 3, they calculate already.
Oh
It
yeah,
has no
yeah, sure.
charge. Then there's 3 neutron, 3 particle emitted. Right? That's energy. Don't have to worry about how to calculate the energy, but you need to know how to write the equation. Right? Distinctive feature, heavy nucleus, two lighter nucleus, emission of usually neutron. Fusion, the difference is there are two lighter one, example, two lighter nuclei joined to form a heavier one. This heavier one with the additional particles, this additional particle, usually this can be a proton or neutron, thrown off to conserve momentum. Right? Or this picture will show you deuterium and tritium combine to form fusion to produce helium and a neutron plus energy release. Okay, let's try some worksheet problem. Right, you have the form data sheet. You can use a data sheet to know where to find your value. What is the rest mass of proton? Can
Where is it?
rest mass of proton? Where to find from the data sheet?
Okay. 1.67 times 10 to the power negative 7.
Okay. Know where to find
Negative
it?
7.
Charge of a proton?
Yeah.
Charge of a proton? Can find it?
Wait, because I'm on iPad.
It's on the diagram. There, on the diagram there. Right?
Oh
Either
yeah.
charge of proton or charge of electron. Okay, refer to the data. An electron is a negatively charged particle of the atom found in the electron cloud. What's the rest mass of the electron? Yeah? Refer to your note. I've sent you the
Wait,
note.
I on
Okay,
iPad I cannot.
you must be ready. Now you're wasting your money.
Okay.
Yeah, that's the rest mass of a proton. Electron, sorry. Rest mass of electron. That's the charge of electron. You should be able to get it from the data sheet. Okay?
Mm.
A neutron has no charge and is found in the nucleus. It has about the same mass as a proton. What's the rest mass of a neutron? Just give it. It's not given a data sheet. Right? Just give it as about that, roughly that of a proton. Right? And you should be able to fill out the table. That's the answer for the table. Okay?
Okay, so neutron and proton same mass.
Roughly lah. Neutron is slightly heavier, but number of significant figure wise will be almost the same lah in this case. Okay with that? You should be able to fill out the diagram, the table also.
Oh, okay.
What is a nucleon?
Mm,
Particle found in a nucleus, so can be a proton or a neutron. Okay?
okay.
Chemical symbol of a nucleus. What does A represent? Yep, can remember?
Proton.
Number of nucleon, mass number,
Oh shit, nucleon.
number of proton and neutron in the nucleus. Z,
Uh,
Z or Z represent,
electrons is it?
yeah, number of protons can be also number of electron. But usually we represent that proton. So number of neutron, we can just subtract A minus Z. Okay,
Mm,
state the number of proton and neutron and electron in aluminium. Okay, I've given you aluminium nucleus, number of proton,
uh, 27.
yeah, number of proton, how many? There, number 13, no? Electron
Eh?
also 13.
Oh yeah,
Number of neutron,
27.
no, 27 is the
27
total
minus
number of
13.
proton and neutron. 14
Minus
neutron,
13.
13 electron.
Okay.
Give an example of the isotope of aluminium. Example of aluminium, isotope of aluminium, give an example.
What example? What do you mean by that?
Give an example. What is the formula? I've given you one, you give me another one. I've given you one already, aluminium.
Oh, you mean another example of the
Give
material, is
another
it?
example. Isotope. Isotope must have the same 13 one. Only the top there is changed.
Oh,
So any number there. Isotope aluminium, it can be there. As long as it has 13, it can be 28, and then or 26, 13. What's the mass of an atom of aluminium? How do you calculate that? Use atomic mass unit,
um,
right? In this example, there are 27 nucleons. Then times atomic mass unit, This is not an isotope, right? 28, 14 is different already. It should be 13, right? 27 atomic mass unit. That's the mass of aluminium. Atomic mass unit converted to kilogram. Right? Use your data sheet to get a conversion. One atomic mass unit is 1.66 times 10 to the power minus 27 kilogram. Use a calculator, calculate out. Can?
yeah, good answer.
Okay, what's the symbol? Identify the following particle.
This one is an electron, is it?
Okay, negative sign electron. Next one,
Nucleon.
neutron.
Oh, neutron, yeah.
Next one,
This one is a proton.
proton, good. Next one,
Alpha particle.
good. That's all. Make sure you know the symbol. That's why I'm going over with you slowly. What's the nucleus of an atom?
Uh,
Okay, it's a tiny but massive center part of an atom. Contains a proton and neutron. Right? That one you must memorize. What's the approximate
oh,
size of
okay.
an atom?
Oh,
Right? Look at the picture. It's already given you in the picture. Right? All this must be in your head. Memorize it. Okay?
okay.
When an alpha particle collides with a beryllium nucleus, a neutron is given out. Write the nuclear equation for the reaction. Okay, you should be able to write that equation. Alpha hit beryllium, a neutron is produced. Write a nuclear equation. Try writing the nuclear equation.
So that one plus 1 0 n.
Eh? Beryllium,
Ah,
alpha, you get carbon and neutron. Okay,
wait, teacher, where does the He come from?
say again. What is it? That's
Where
your
does the
beryllium.
helium come from?
Alpha particle. This alpha particle.
Oh, yeah, yeah, okay.
Then you got neutron. So that's your
What about
carbon.
the
No?
C?
Right? The top add together 13, 13. Bottom add together 6, 6. Oh.
Uh, that was, oh, then you just find it from the periodic table, is it?
Usually they expect you to be able to recognize carbon. Nah. If they if they don't expect
Oh,
you, then they will tell you it's carbon. No? Carbon is produced. But you should be able to write
okay.
the Z number and the A number, number of nucleon, proton number, must be able to write that. Right? This is the experiment and how to detect neutron. You pass it through paraffin wax. Oh. Okay, bother about that. Okay, we try one more. Try number 1. Write a nuclear equation, complete the nuclear equation. What's the answer? Yep, what's the answer? You don't need to call, just put it XO. The chemical formula give you an XO. Chemical symbol put
Oh,
an
okay. So,
What's your A? A
two
or
three
X?
eight
What is your Z?
92.
Ah, that's all. 92, 238. The rest you can try yourself.
Okay.
Okay, anything you want to ask? If not, we just carry on with properties of radiation. Yep. Anything else you want to ask?
Yeah, can carry on.
Carry on. Page 273. Right, suppose you have a source, radioactive source that produce alpha, beta, and gamma, and then we place it in the uniform magnetic field. Sketch the path. Right, so you should be able to sketch the path. So which one is alpha, which one is beta, which one is gamma? Yep.
Mm-hmm.
Which of identify which one is alpha, which one is gamma, which one is beta?
The first line, the top line is alpha,
Then the center line.
gamma.
Mm, good. Right? Beta being very light, easily deflected by the magnetic field.
It's
Gamma is not deflected by magnetic field. Right? It goes straight through. So we can use magnetic field to separate the rays. Alpha and beta rays are particles. Gamma rays are radiation, that is electromagnetic radiation. And then we can pass it through, there's a lead block, there's a radio source. So we are going to finish in 10 minutes time. Let me see whether there's a lot to cover. Okay lah, we'll try to cover the rest next week lah. Sorry, tomorrow lah. So let's cover as much as possible. Right? Theta or radiation,
okay.
you should be able to.
Wait, teacher.
Yep. Yep. What's the problem?
So we are covering this one and uh chapter 2 tomorrow.
Tomorrow we will go to we will finish this one types of radiation which we are not able to complete. Then we will go into quaxo, fundamental particles. Okay with that?
Oh, how?
We may have to go an extra time lah, 10 to 20 minutes lah, as usual.
Okay.
Okay with that?
Yeah, sure.
Beta is usually electron, so it's easily deflected. Gamma is not affected by electric field. Right? So using electric field to separate the rays. Right? Alpha, what is alpha? Particle, helium nucleus. Right? That's how we represent it. Helium has lost 2 electron or alpha for 2. Speed, is about roughly about 10 to the power 6 meter per second. Discrete value of energy, that means 1 or 2 energy lah. Right? Doesn't have a continuous range of energy. Ionizing power, very high due to large charge. Mass, it's about 4 atomic mass unit. Charge, 2 positive charge. Range, 5 cm. Stopped by paper. Affected by electric and magnetic field, yes. Okay with that, you should be able to know what is alpha. All these are memory work lah.
Yeah.
Beta minus, what is it? Particle, high speed electron. That's how we represent it. It's not a nucleon, that's why it's 0. Right, the top there is 0. Speed, 10 to the power 8 meter per second. Continuous spectrum of energy. Right? It's near the speed of light lah. Ionizing power, moderate due to low charge. Right? Whereas alpha is huge, much larger mass than electron, so it has more ionization. So this is moderate. Mass, about 1 over 2000 atomic mass unit. Charge, negatively charged. Range in air, about 1 meter lah. Stopped by 3 millimeter of aluminium. All this memory work lah, nothing can teach you. Affected by electric and magnetic field, yes. Okay. Stop me, going too fast.
Okay.
Electromagnetic radiation, gamma, symbol, speed of light. Usually discrete also lah, like alpha. Ionizing power, very low. Low due to no charge, yes, no charge. Mass, no mass. Charge, no charge, neutral. Range in air, very large distance, can travel very large distance. Stopped by about by several meter of concrete or lead. Not affected by electric or magnetic field. Okay, so you should be able to fill up this distinguish between alpha and beta and gamma. Right? Alpha is helium nucleus, gamma electromagnetic
Yep.
radiation. Speed,
Speed of light.
about 0.01 speed of light or 0.1 speed of light roughly roughly 10 to the power 6 meter Whereas beta is about it can be up to 99% the speed of light Gamma speed of light, energy discrete, energy continuous spectrum of energy. Right? For gamma also discrete Very high ionization, ionizing power very high due to large charge and large mass. For beta is moderate due to low charge. Gamma no charge at all, so it's low ionizing power. Right? We have done that, so we just fill out the table, that's all. Gamma, no mass, charge. Sorry, it should be 2E or alpha. Right? Beta is minus E, gamma, no charge, range. Alpha is very much less than beta, and beta is very much less than gamma. Gamma is the longest range. Right? In terms of actual value is 5 cm in air or 1 meter for beta, gamma large distance. Stored by paper for alpha, for beta 3 millimeter aluminum, for gamma several meter of concrete or lead. These are all memory work, nothing can teach you. Yep. Anything? Yep. What is the problem?
Oh, I got learn some before.
So I go faster. Right? Alpha and
Uh,
beta deflected by
no,
electric.
for,
Yep. Sorry. What's the problem?
nothing.
Gamma is not affected by magnetic field.
Nothing.
Alpha emission question. What happened to the A? Nuclear number lah. What happened to the nuclear number in alpha decay?
Uh,
Okay?
decrease.
Decrease by 4. A decreased by 4.
Ah,
And then how about Z?
like decrease
Okay?
by 2.
That's all. You must memorize that.
Okay.
Many alpha emitters produce alpha particle of one energy only. Alpha particle is said to be monoenergetic. That means one energy only. And they have very nearly equal range in any particular absorber. Right? Nearly equal range because they have the same energy. A, the nuclear number decreases by 4. Z, the proton number decreases by 2. Memorize. Right? As far as
Mm.
alpha decay is concerned, there's
So
a
it's standard all the alpha is decrease.
say again.
So
Say
it's
again.
standard.
It's standard.
It's standard, right?
There's a original mass. If it's stationary, U is stationary, no speed. Then it's straight. One will go to the left, or one will go to the right. Right? So that will be radon. That will be alpha. And then we can apply the conservation momentum. Some momentum initially, some momentum finally. Initially is a total mass. Right? Right? If we add this total mass as M, and then initially is